And we're starting out with a bit of revision on the states of matter. So for states, for our purposes, there are three states of matter: solid, liquid, and gas. Yes, there's plasma, but plasma is not normally encountered in our everyday lives. And if you look at the table on page 3, we can see there's a bit of a comparison of the properties of solids, liquids, and gases. Solids are high density, and they have a fixed volume. We can model them like this, can't we? As being close together in a regular arrangement, and the shape doesn't change. So if I put that into a beaker, it stays the same shape. It's not going to change. And each of these, all they can do is vibrate in their position that they are within the solid. And, compressibility, can we squash it? Pretty well no. And will it mix? No, it doesn't mix very well. So if I happened to have another solid sitting on top, I come back a year later, it's probably still sitting on top. It's not going to mix together. Liquids, still high density. This time though, my liquid is going to take the shape of the container. It still has a fixed volume and is practically incompressible as well. You can't really squash them any closer together in practical terms than they already are. Will they mix? Well, they will mix, but it's reasonably slowly. You could have, depends on the amount of energy given to the system, how quickly it will mix together. So if we heat it up, then we'll have convection currents that help mix them together. But otherwise, it's reasonably slow. Certainly this is very slow, as in almost doesn't happen. This is slow, but we're really interested in gases. That's what we want to look at. Gases will occupy the whole container. And they have a low density. They'll fit the shape of the container, and they are easily compressed. We can do it. So if this was a plunger from here, we would be able to squash that down, make the particles closer together. And they mix rapidly. So if I put some gas particles in at the top there, it wouldn't take very long at all for them to then be evenly distributed throughout the container. Let's see if I can't demonstrate this a little bit. I found this in the bathroom at home. Nobody wants to use it. Rexona men. Certainly doesn't appeal to me. But if I spray some, let's see how long it takes you to smell this lovely scent. Oh. In a way I can tell why no one wants to wear it. Can anyone smell it yet?
Yeah.
You can already. So that shows how rapidly gases can move through the air. Right. Now we're going to focus on the way the particles move. The way we model gases is that they are very small particles, and that's reasonable. They are very small particles. And they are separated from each other by very large distances. So an example of that would be, let's think about the air. Okay, so we're going to think about air that we're currently breathing. If I were able to compress down so that there were no spaces between the molecules, so this is representing my air, most of which is nitrogen, H2 gas. How much, what volume, what percent volume do you think it would occupy compared to before it was compressed? Okay, so I start out with 100% volume, and then I squash it down until basically I've made a liquid. What is the volume of that going to be compared to my original one? Just guess. This is not something you need to learn or memorize or anything. I just want you to ballpark tell me, because this is giving you an idea of how far apart they actually are, the molecules. 50%. Okay, we've got 50%.
Would it be 100%?
100% means that there's no gaps between the particles.
And so you're very compressing it.
I'm compressing it until they're touching, so I make a liquid. You know how you have liquid nitrogen, liquid oxygen? How much? I'm going to say it's compressed air down to a liquid.
Can you get a bar of law?
Lower. 20?
Less than
Less than 1%. Where do people think we've gone from 50% down to less than 1%? 0.1% of the volume is actually particles. All the rest of it is empty space, i.e. nothing. That's what we're currently breathing. So there's a whole lot of empty space. And this is the case for most of what we see with gases. If only 0.1% of it is actually the particles, so the solid part of gases, then that explains our next bit of modelling for gases, and that is we assume that they behave as if they are by themselves. They don't really, there's not a lot of interactions because there's so much space between them. So what this means is that I can have this gas, and I can have this gas, and these gases, and I can model them all the same way, because it doesn't matter that they're different gases, they behave the same. They mostly behave the same, because there's very few interactions between them. The other thing we can say is that they are high-speed particles. Okay, they travel at high speeds. They travel in straight lines until they hit something. And then the laws of physics will take over and they'll bounce off with an elastic collision. Okay, all of the collisions for gases are elastic. Can you remember what that means in terms of what is conserved? Kinetic energy is conserved. Okay, so we've got our high-speed particles that travel in straight directions until they hit something, and then they bounce off according to the laws of physics, and they undergo elastic collisions either with each other or the container that they're in. And so, if we've got a number of particles present, we can also say that really their motion is random. They're not all moving together in the same way, which is a good thing. Because imagine if we came into this lab and all the oxygen had decided to move to that corner of the room and leave the nitrogen over here and the carbon dioxide. Well, we'd all die, wouldn't we? It would be a really strange scenario. So it's always mixed up, evenly distributed, but the particles themselves are moving in random way. And we can determine the pressure. The gas pressure is all to do with how many collisions we have in the container. And that's what the gas pressure is. So the more collisions we have, the greater the pressure. If you turn over to page 4, there's a little bit of a summary of the kinetic theory of gases. Now, remembering that this is Criterion, so we're going to be using this to explain the properties that we see. So, low density, gases have low densities because there are large areas of unoccupied space. Volume and shape. These gas particles have high speeds and they can quickly move around to take up all of the available space. They are compressible because there is a lot of space. We can push those particles closer together. They mix together easily because they are all high-speed particles moving in random directions, and they're all going to then disperse throughout the container. This is actually called diffusion. What I did with that deodorant spray there was gas diffused throughout the air in the lab. Now, when we're talking about gases, we describe them as, we use this model of the ideal gas. So just like the ideal partner doesn't exist, neither does an ideal gas. but you can understand the properties by thinking about it. So an ideal gas. And we have this model of an ideal gas because this allows us to do calculations. Okay, so this page here with the kinetic theory of gases, it's still Criterion 7, and it's probably the important one that for you to refer back to when you're preparing for the assessment on C7. We've already talked about gases being small particles. They're either atoms or molecules, aren't they? Which ones are going to be atoms? The noble gases. They are going to be atoms. The rest of them will be molecules. So the size of the gas particles is really small, and if you think about the total volume, then the particle itself takes up a very small percentage of the available space. And so therefore a gas here, like you have at the moment, is mostly empty space. Gas particles can travel throughout the whole volume of the container. They move in straight lines at high speed. Okay, now, high speed is an average. That means that some might be slow at some point, mightn't they? Because if I'm a particle and I'm colliding with the wall and I'm changing direction, what happens in that instant when I hit the wall? Not moving. You've got a very short space of time where you're actually stationary. But then it's going to, this is an elastic collision with something high speeds. So the average speeds are high. The intermolecular forces between gas molecules under certain conditions is negligible. And the certain conditions where it's negligible is relatively high temperature, or not low temperature, and not low pressure. Not high pressure, sorry. Okay, so we could also think of this as like high temperature, low pressure. Is when all gases will behave in a way that is quite close to ideal. Now, if we increase the temperature, we are going to increase the motion of the particles, and that has a flow-on effect to increasing the pressure. Okay, so let's have a little bit more of a look at gas pressure. Pressure is equal to the force divided by the area. So the area of the container, and the force is the collisions of the gas particles with the walls. If we heat up the gas inside the container, then the particles will have a greater amount of kinetic energy. They will move more quickly, and they will hit the wall more frequently as well. So they'll be hitting more frequently, and they'll be hitting harder, so the pressure will increase on the container wall. What else do we need to say? I've got a picture here on page 6, and it's a metal can that's been connected to a vacuum pump, and the vacuum pump is removing air. So it's taking away the gas particles from inside the can. Then what happens to the can? What's happened to the can in the picture?
It gets crushed by the difference in air pressure.
It does. So the way we can think of this is if this is my can, that's just the can before I started doing it. All of the collisions of my molecules in the air, atoms, are going to be matched by collisions on both sides of the container. Okay, because the container, so the pressure is the same because we've got the same number of particles pushing on either side of the wall. But if I then take the gas particles out of the container, I'm going to close the lid. And it's very hard to remove them all, so I've left a couple in there. Look there, there's going to be a tiny amount of pressure on the wall from those two remaining dots in my can. And then I still have the same amount of air pressure on the outside that is going to crush the can. Okay, so just like we said, it's all to do with the difference in pressure there. The air pressure, we're actually under quite a lot of air pressure now, but because we live with it all the time, we don't even notice it. We've got here, with the can open, pressures on either side. Here now, with evacuate the container, close the lid, it will crush the can. Okay, and then on the bottom of page 6, we've already talked about diffusion, which was the deodorant here that spread quickly through the room. And as it says here, this is why you can smell cooking smell or other odours travel around quite rapidly, and someone could be cooking something in the kitchen and you can smell it down another end of the house. Okay, and one more thing to talk about on page 7, and that is this difference between real and ideal gases. So I said that there is no such thing as an ideal gas, but we can use this idea to approximate most gases as long as we're in reasonable temperatures, not too low, and low pressures. So what happens then if we change those situations? What happens if it's low temperature and high pressure? Low temperature, what's that going to do to the kinetic energy of the particles? Reduce. Yes, so this will reduce the kinetic energy. What does high pressure do?
It makes the particles closer together.
Yeah, brings them together. So now we're taking away those important properties of the ideal gas. And what happens is that if they get close together, there will be some interactions. And they are going to attract each other. So if you look at the diagram on page 7, you can see that the ideal gas, if I brought two molecules or atoms of the ideal gas really close together, then they would not interact, they would not attract each other. But the real gas molecules do attract each other. So under these conditions, we have attraction between the gas molecules. And what do you think that is going to do to say the volume that it would take up? What would be the difference between the volume of a real gas compared to the volume of an ideal gas under these conditions? In actual, yes, that's right. So the real gas will take up less volume because we've got more attractions than we had in ordinary gas. Can also liquefy it at a higher temperature than we would calculate. Don't have to take away as much energy as we would think because we're starting to get these interactions between them. Okay, so these are, if you like, extreme conditions, and this is where gases will deviate from that ideal behaviour. Helium is the most ideal gas, or the gas that best approximates an ideal gas. Why do you think that is? Why would helium be a real gas that
It doesn't really attract to each other very much, and it's got a very small atomic radius.
Yep, so monatomic, non-reactive, small. So all of that means that this is much less reactive than our hydrogen. And so it's also quite a lot smaller than an neon. So helium is close to the closest thing that exists to an ideal gas. Okay. I believe you're now to looking at answering some questions in the booklet.